Okay, thank you. Hello, everyone. First of all, I would like to thank the organizers for giving me the opportunity to give this talk. And it's a shame that I couldn't make it to Granada. So anyway, let's get started. Today, I want to tell you about my joint work with Emil Akhmedov. The links are given here. Actually, I forgot to write here my email. So the email is in this paper. And well, you can maybe contact the organizers if you want to discuss something. And well, write me if you want to discuss something. I'll be happy to discuss. Today I want to tell you about the toy problem we have considered, in which we considered the problem of counting the number of created particles in the in cosmology. So let me just stress that today I will tell you about two-dimensional geometry, and all the results I will tell you about can be generalized to the arbitrary number of dimensions, so it's not just fixed to 2 dimensions. Well, just for simplicity, we'll just stick to 2 dimensions. So the geometry is given right here is just the example which is written in the Birrell-Davis textbook. We have the expanded geometry from one asymptotically flat region to the another. So the rich scalar is expansion dumped in these 2 asymptotic regions, and we have just 2 flat space-time and just a smooth expansion of the geometry. We want to consider the simplest theory we can write is just the scalar field theory with the quartic self-interaction. And one of the reasons why we consider this geometry is that the equation of motions for free fields can be solved exactly in this space-time, and one can distinguish these solutions, which are called in-modes, which are given just by the product of exponentials by the Gaussian hypergeometric function. So the distinct property of this in-modes is that it has the plane wave behavior in the asymptotic past, and just is given by the linear combination of plane waves in the asymptotic future with the coefficients given here. One way to quantize our field is just mode expand our field with respect to these modes, in-modes, and here we define the creation and annihilation operators for the in-modes A and A diagram. Another way of quantizing our field is to solve our equation of motions and to distinguish the solutions which are the out modes, which are given here, and they have the similar behavior. They're plane waves in the asymptotic future, so they diagonalize the Hamiltonian in the asymptotic future, and they're given by just the linear combination of plane waves in the asymptotic past. So alternatively, we can quantize our field using these out modes, and here we define the creation and annihilation operators for the out modes. And now I'm telling you about the results in the free field theory, and then I will discuss what I did in my research, and what happens if we tune in if you tune on the interactions. So we can equate these 2 mode decompositions and obtain here we just obtain the following relation between creation and annihilation operators with the Bogoliubov coefficients given here, and these Bogoliubov coefficients will just give you the rate of the created particles, which is given here. So what happens in these situations? We start with the Fock vacuum in the asymptotic past, which is the Fock vacuum for the in-modes defined here. And we assume that in the asymptotic future, our state of the system is given by the out modes, which are defined here. So if we take the average of number of in modes particles with respect to this out modes vacuum state, we obtain that this quantity is given by this integral of this Bogoliubov coefficients, and this integral is in fact this is the finite number, and so we have that in the free field theory. The number of created particles is just a finite non-zero number. So now we want to consider the interacting field theory, and I want to show that the number of created particles from the interactions cannot be can be substantial and not suppressed by the interaction constant, with the coupling constant. So, but before that, let us consider example of a scalar field in the flat space-time. Here the modes are just given by this simple plane waves in the whole space-time. So if we consider Schwinger-Keldysh diagrammatic technique, which we need to, because in our setup, our final state of the system is not well, does not coincide with the initial state. So if our final initial state does not coincide, then we cannot use the Feynman diagrammatic technique, right? So we use the Schwinger-Keldysh diagrammatic technique and write down the loop corrections to Keldysh propagator. And if we sum all the circularly growing loop corrections, write down the Dyson-Schwinger equation for the Keldysh function, and then we can rewrite this equation as a kinetic equation for the occupation numbers, which is given here. And here we see that in the flat space-time, if we start from the non-equilibrium state, we have just, well, thermalization, because one can see that this collision integral is solved by the thermal distribution, and also, in fact, with the Fock vacuum state. So if you start with the non-equilibrium state, in a flat space-time, we have just the collisions of two particles, and because of these collisions, our system thermalizes, and we have this just the equilibrium final state. So we want to see how this formula is, well, how this formula is written in the expanding geometry. So we write down, we tune in our interactions in our system. We will just take the quartic self-interaction for our field. Well, technically, we have the two types of vertices in our theory, and on a Schwinger-Keldysh contour. And so let's start discussing the loop corrections from the tadpole diagrams, which are the diagrams depicted in here. So if we take the infrared limit, well, eta1 and eta2 are the temporal coordinates of these two endpoints of these diagrams. If we take the infrared limit, we can write down the Dyson-Schwinger-Keldysh for the exact Keldysh function, the exact being the Keldysh function, which accounts for all these tadpole diagrams. The exact Keldysh function we denoted by the GK with tilde. The equation, that Dyson-Schwinger equation, will be like this. And if we apply a differential operator box plus m squared to do both sides of this equation, we obtain the following equation for the exact Keldysh function. From here, we can see that the tadpole diagrams, some of them from all orders, is just leads to the mass renormalization ultraviolet, because here we have the Keldysh function in the coinciding points. And also this well, Keldysh function coinciding points here also contains the non-local part, which just renormalizes the wave functions, and well, the renormalized wave functions have this following form, but it's not very sufficient for our considerations. So the most interesting part is these sunset diagrams, because well, you'll see it in a minute. We can write down the two loop corrections to the Keldysh function, which is just all these diagrams. And if we again take the infrared limit, eta1 plus eta2, well, we take it much larger than their difference, then we can write down the loop corrections to the occupation numbers using this formula. Here we have the definition of Keldysh function, and we write down the mode decomposition, and we obtain that the Keldysh function generally has the following form. So we interpret the loop corrections to the Keldysh function as the loop corrections to the occupation numbers A dagger A, and anomalous quantum averages AA and A dagger A dagger. So again, we take the infrared limit, And we obtain that the loop corrections, two loop corrections to the occupation number have the following form. Here, first of all, here that we can see that as opposed to the flat space-time example, here we have much like richer structure of the collision integral, because we have not only collisions of two particles, but also like creation of four particles from nothing, and also annihilation of four particles, decay of one particles in three, and so on. And another more important point from this formula is that this expression contains eta as a prefactor. So from here, one can see that even if the lambda, our coupling constant, is small, we can wait long enough and see that our loop corrections to our physical quantities are comparable to our tree-level results. And there is a widely held perception that because the coupling constants are small, so we cannot, we should not worry about the loop corrections, because anyway they can contain the coupling constant, so they overall their contribution is small. So here we see that this is not the case, in fact, because these loop corrections contain secularly growing corrections, which can give substantial corrections to the tree-level results. The same holds for the anomalous quantum averages. We obtain that they're also growing with time, and that's that. Yeah. Here I was talking about the in modes while we quantize our field using the in modes. The same can be done using the out modes, and we obtain that in the infrared limit in the distant future. We obtain this just the usual flat space-time equilibration, like this collision integral. So now let us talk about the stress energy tensor. We can regularize it using Pauli-Wheeler's regularization scheme, and by implying the condition that our stress energy tensor goes to zero in the distant past, we can obtain the following result. Here we have the T mu 0 and T mu loop. T mu 0 being the answer which we would obtain if we wouldn't have the loop corrections to anomalous averages and occupation numbers, and also these loop corrections that contain this nk and kappa k. Here, quantum averages and occupation numbers are growing with time, so we also obtain that our stress energy tensor also grows with time in this setup. So this signalizes that the back reaction on the geometry should also be substantial if we consider the interacting field theory. So as I said, it has been shown that occupation numbers and quantum averages grow secularly, and these secularly growing loop corrections, more importantly, they are not zero if we take the Fock vacuum. If we take n equal to 0, this collision integral is not 0. So the secularly growing loop corrections here are here, even if we start with the equilibrium situation. So also we can see that the stress energy tensor also is growing secularly, and also that also as I mentioned earlier, this analysis can be generalized to the general arbitrary number of dimensions, and the next step will be to sum all the secular growing loop corrections. Here for the sunset diagrams, we just restricted ourselves to the two loop analysis, and if we take the if we want to consider all the orders of perturbation theory, we have to sum all the secularly growing diagrams. We again write down the Dyson-Schwinger equation for the exact Keldysh functions, and we sum all the diagrams, and we obtain how the exact state of the system changes with time and how it back reacts on the geometry of the space-time. So thank you for your attention. Yes, that's all.
Okay, thank you very much for your talk. I think we have time for one question, maybe. So, okay, yes, we have one question.
Hi, can you hear me?
Yes.
Okay, thank you for your talk, first of all. And then I have the following question. So if I well understood the point, you are here evaluating the correlation functions using the Keldysh-Schwinger formalism, right?
Yes, yes.
And you found out somehow that you have this kind of secular growth in time, even if you start with an equilibrium state. Like
yes, yes.
Okay.
Because well, our geometry, we have the flat space-time here and flat space-time here. So the state of our system should inevitably change. So that's the result we obtain, which is
okay,
and physical ground also well. Yeah.
So my question is the following, because actually the assumption of starting with an equilibrium state for an interacting theory, starting with an equilibrium state of the free theory and evaluating the expectation value of the interacting observables, which is equivalent to the Keldysh-Schwinger formalism, corresponds somehow to neglecting the effect of the interaction at the level of the state. And this is, in some situation, it's okay, like in many situations, because there is this condition of return to equilibrium that somehow guarantee that the state will automatically end up to be the equilibrium state of the interacting theory. But there are also a lot of situations, like the thermal situation, for instance, and many more situations in quantum field theory in which this principle is actually no more valid. And neglecting this problem, of course, is what leads to this growth in time. If you actually really use an equilibrium state for the interacting theory, this kind of time evolution shouldn't, time growth shouldn't be there. And this kind of taking in consideration the effect of the interaction on the state is somehow mixing the Keldysh-Schwinger formalism with the Matsubara formalism, which is the opposite. So I wanted to know if you somehow consider this problem, that the state could be not the correct one.
No, well, that's a very interesting question. Well, I haven't thought about it, but well, as we are considering all in the perturbation theory, I guess I guess that the equilibrium interaction state will for this setup in which we're calculating all of these quantities, it's not necessary from my point of view.
Okay, thanks